All right, so we're going to continue with chemical kinetics today, and I didn't have your learning goal up yesterday because you had finished the test. So we're going to define kinetics. We're going to write and solve rate expressions. Yesterday we did define kinetics, the study of reaction rates and the factors that affect them. We learned how to write rate expressions, which we'll review in the do now. We'll be solving them today, and you'll also learn how to write rate laws today for very simple problems. The kids usually like that the best because it's very math related. We'll be then discussing the collision theory, and then we'll also look next time at factors that affect reaction rates. So this is your do now. I can make it a little bigger. Should take you just a couple minutes to write a rate equation or expression that shows the disappearance of an element and the appearance of a compound. The piece underneath we'll hit later. So take a minute to write that rate equation. Bless you. And just be very careful with what you select. The problem is specific. Yes, yes? Yes? Okay, so you do, of course, have to balance the equation. And again, those of you sitting in the back, make sure it's big enough, and if you want to move forward, that would be fine. What? You have to balance the equation, and then just be careful, like I said, with what you selected here, because the question called for the disappearance of an element. So do reactants or products disappear? Reactants, because they get consumed. So why did I use a -1 there in that first fraction?
Because when you do a -1 times a reactant, it makes it positive.
Right. So whenever you have a reactant, you have -1 over its coefficient, and as Chloe said, you use the -1 because what goes in there will be negative, which you'll see momentarily. Then it said, and the appearance of a compound. So you have to find a compound on the product side, +1 for product over the coefficient 3, change in concentration of calcium fluoride over the change in time. And as a reminder, lowercase t for time, uppercase T is temperature. So be careful there, you'd lose a couple points on your quiz if you did that. And we're looking to quiz next week, and we'll try and really iron down the date. I think it will be, I think it'll be Wednesday, just for a quiz. Next week on Wednesday, I think. But it's a little tricky with this odd, odd, even, even. So we'll figure out what works best for you and run with it.
Yeah,
okay.
The 21st and 25th. I think it's those two.
Right. So I think I'd be looking at your quiz the 20th because I don't want to hit those algebra dates. Yes. Okay, so you know how to write rate equations or expressions. We want to solve them. This is very, very basic math. You'll be very good at this. If we flip over then to our notes, what we want to look at now is how to solve them. Most chemical reactions do show changing rates. The same way if you were driving to Disney World, you wouldn't just get in the car, hit cruise control the whole way and get there. You probably are going to take a bathroom break, and some of you like a donut break and things like that. So you have to get off the highway where your rate will slow, and then you'll stop. Then you do what you need to do in the rest stop. You get back in the car, you accelerate, constant rate again until you get to your destination and you slow. So same thing with chemical reactions. They'll start slow, they'll speed up, they'll level off, and then they'll slow down as you use more and more reactant up, especially with the limiting reagent. It would be used up completely, and then you'd have nothing left to react. You can calculate the rate of change for a substance, and you can do it either from a rate equation and or from data, and that's what we're going to be looking at here. So basically what's going to happen here, if we refer back to your do now, is that you might be given the rate at which calcium disappears, and you'll put that rate in here, and then you'll solve for the rate at which calcium fluoride appears. So you'll work your rate equation throwing data in that you've been provided. For example, if we look at the decomposition of dinitrogen pentoxide to nitrogen dioxide and oxygen gas, if it says the rate at which nitrogen dioxide, a product, forms is 0.0072 molar per second, we want to know the rate of change for the oxygen gas. So in green is what's given, and I can more simply write it in this regard. I'm looking for the rate of change of oxygen gas, shown here with the question mark in yellow. I set up a rate equation with those two substances, just like from the do now. Product, positive 1 over the coefficient 4. Product, positive 1 over the coefficient of 1. Change in concentration over the change in time. So the new piece is going to be putting that data in for the rate at which NO2 forms. So I'm going to replace this piece, and yes, you usually replace the whole fraction, so you're not solving for denominators or anything like that. 0.0072 molar per second. And now you're going to solve for the oxygen rate change here. And again, you've got 1 over 1, so that's just 1. You're going to solve for this piece. 1/4 of 0.0072 is 0.0018 molar per second. Very straightforward. And we'll do the next one from scratch.